one of the most well-known experts in advanced physics, has expressed his opinion on the matter. Michio Kaku, recognized for his outstanding contributions to the field, recently confirmed that the James Webb Space Telescope has discovered 6 massive galaxies that scientists previously thought could not exist. The potential for these investigations to expand our scientific understanding of the universe is both exciting and revolutionary, challenging existing theories about the formation and emergence of galaxies. As a result, it is worth keeping an eye on these developments. The confirmation by such a notable scientist as Michio Kaku emphasizes the significance of these findings. Michio Kaku is an outstanding figure in the scientific community, a physicist of American and Japanese heritage, regarded as an expert in both classical experimental physics and quantum mechanics. Unlike some skeptical and conservative scientists, Kaku does not belong to that group. He has been receptive to the amazing findings of the James Webb Space Telescope's mission. His willingness to embrace new discoveries and share them with the public highlights his commitment to advancing our understanding of the universe. We are pleased that this accomplished scientist has chosen to speak publicly, breaking his silence on a matter that can no longer be denied. His enthusiasm, even an almost amused tone, is evident in his comments on this discovery. The James Webb Space Telescope's findings have piqued his interest, leading him to explore the implications of discovering these 6 massive galaxies. Kaku has always been willing to consider new theories. Throughout his life, he has demonstrated an openness to ideas that challenge the status quo. Given that Einstein's, Newton's, and the laws of relativity, while foundational, are insufficient to capture the full complexity of the universe, Kaku understands that these new telescope discoveries have the potential to enhance scientific knowledge. Despite this, many of his colleagues have struggled to adopt this perspective. The discovery is generating concern and insomnia among both supporters and opponents of the Big Bang and quantum mechanics. However, this only amuses Michio Kaku. The James Webb Space Telescope has revealed the discovery of 6 massive galaxies dating back to the earliest times of the universe. Each of these galaxies contains more stars than our own Milky Way, despite forming only 200 to 700 million years after the Big Bang. The team of astronomers responsible for the discovery has given these galaxies the name universe breakers, because, if confirmed, they would revolutionize our understanding of the universe. The implications are profound, suggesting that the early universe was far more dynamic and complex than previously believed. There seems to be a contradiction here. According to the Big Bang theory, the cosmos was initially a chaotic state. It took hundreds of thousands of years for solid structures to form, and even hundreds of millions of years for them to reach an adequate density and produce complex structures like galaxies. Some of these newly discovered galaxies surpass the Milky Way in size. Their immense luminosity suggests they were likely forming hundreds of new stars each year, whereas our own galaxy forms stars only sporadically. It remains uncertain precisely when the first galaxies formed. Researchers have not yet determined this. The only clear fact is that the earliest cosmic structures may have initially consisted of single stars or groups of stars that later merged, forming increasingly larger structures over time. Dwarf galaxies likely developed first, eventually colliding with others and growing into larger galaxies. Previous theories suggested that well-organized massive galaxies could not have existed so early. This raises a fundamental question. Is the universe much older than previously thought, or did complex galactic arrangements develop much earlier than expected? This situation is difficult for conservative scientists to accept, as it contradicts established models. Some physicists strongly refuse to accept these findings, questioning whether errors were made in age calculations. Michio Kaku acknowledges this resistance and points out that history is filled with old, false theories that persisted merely due to the prestige of their proponents. These theories were ultimately disproven when crucial experiments revealed their flaws. The fundamental role of any science, especially physics, lies with experimentalists who hold theorists accountable. In reality, we still know very little about the true beginnings of the cosmos. This quote from Kaku underscores the importance of continuous experimentation and validation through the scientific method. The Big Bang theory was formulated in 1927 based on observations of the universe's expansion. These data led to the conclusion that the cosmos originated from a single point and has been expanding ever since. Initially, both scientists and the general public struggled to conceive of a universe with a beginning and an end. The idea that the universe had always existed, infinite in space and time, was deeply ingrained. Even today, many scientists grapple with these concepts. Nevertheless, it is crucial to reconsider these possibilities. The new evidence does not align with what researchers have accepted for decades under the Big Bang theory. However, science has repeatedly demonstrated the necessity of re-evaluating and being open to new ideas. Historically, certain hypotheses were once considered unshakable until new findings emerged. When Einstein was young, people believed that planets and stars were fixed in place. We now know that everything in the cosmos is in motion. Planets orbit stars, stars move within galaxies at hundreds of kilometers per second, and entire galaxies travel rapidly through the cosmos, their fate still uncertain. This evolving understanding of a dynamic universe challenges long-standing beliefs and highlights the need for continuous research and adaptation in scientific thought. Scientists today must confront uncomfortable truths, recognizing that theories are not absolute truths. They must be rigorously tested and validated through precise observation. The Big Bang theory was largely built upon the realization that galaxies are moving away from each other, with this distance being proportional to their separation. This observation, known as Hubble's law, has supported the idea of an expanding universe for decades. Additional evidence, such as cosmic background radiation and redshifts in distant galaxies, also reinforce this model. However, it is essential to remember that historical misconceptions, such as the belief in a flat Earth or the geocentric model, were once considered valid due to available evidence. Only advancements in technology and more precise measurements disproved these erroneous beliefs. We may now be witnessing a similar paradigm shift. Scientists expected the James Webb Space Telescope to confirm assumptions about the Big Bang, but instead, they have encountered 6 galaxies that seem to defy established models. This serves as a reminder that science is always evolving, and researchers must remain open to new discoveries. These unexpected results challenge existing understanding and compel a reassessment of long-standing cosmological theories. Scientists use redshift as a crucial tool to measure cosmic distances and velocities. Redshift, also known as the Doppler effect, refers to the change in the color of light as a source moves relative to an observer. To illustrate, imagine standing still as a car approaches. As it nears, the engine noise grows louder. Once it passes, the sound diminishes. This shift in sound frequency mirrors what happens with light. When a light source moves toward us, it shifts toward bluer hues. When it moves away, it shifts toward redder hues, a phenomenon known as redshift. Physicists have used redshift to estimate distances and speeds across the cosmos. However, small errors in these measurements could have significant implications. The techniques previously used to measure cosmic distances are now being re-evaluated. It will be fascinating to see what conclusions scientists reach regarding the latest cosmic discoveries. Now, the key question remains: are these new findings the result of measurement errors, or are some researchers simply refusing to accept new realities? This question requires thorough investigation and careful review of data and methodologies. The ongoing scrutiny and reconsideration of cosmological models demonstrate the dynamic nature of scientific inquiry. Measurement techniques highlight the evolving nature of scientific inquiry. Thank you very much. As always, thanks for watching the video. We remind you that you can post your doubts in the box marked "Comment." If you enjoy the video, do not forget to hit the like button to share it with more people and subscribe to the channel so you won't miss any more of this kind of content. Thank you so much for watching, and see you. You should follow up with this call to action. It encourages viewers to engage with the content, fostering a community of curious minds eager to investigate and comprehend the most recent discoveries in science. The study of the vastness of our universe and the complexity of celestial bodies continues to captivate and challenge researchers from all over the world. Theories of the universe have evolved before recent discoveries made possible by modern technology. Every revelation changes how we perceive the universe and pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are cosmic cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is crucial not only for locating the answers to our universe but also for confirming or challenging existing theories, such as the Big Bang theory. The Big Bang theory, formulated nearly a century ago, suggests that the universe originated from a singular, infinitely dense point and has been expanding ever since. This concept emerged from observations of the universe's expansion and the cosmic microwave background radiation, thought to be traces of the earlier universe's intense heat and light. Nevertheless, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang theory. With its first-of-its-kind sensitivity and resolution, JWST has found galaxies that defy conventional understanding. These galaxies, dating back to just a few 100 million years after the Big Bang, are unexpectedly massive and luminous, suggesting a more dynamic early universe than previously imagined. The repercussions of these findings are profound. They raise concerns regarding the timeline and mechanisms of galaxy formation, forcing researchers to re-evaluate existing models. For instance, the discovery of galaxies that are already highly evolved shortly after the Big Bang challenges the notion that galaxy formation was a slow and gradual process occurring over billions of years. Moreover, JWST observations have highlighted the complexity of galaxy evolution. It is now clear that galaxies can expand quickly and serve as crucial sites for early star formation. These insights compel astrophysicists to revise their theories on how stars, gas, and dark matter interacted during the early stages of the cosmos to form the first galaxies. Beyond revolutionizing our understanding of galaxies, these discoveries underscore the critical role of technological advancements in pushing the boundaries of astrophysical research. The JWST, with its infrared capabilities, allows scientists to peer deeper into space and further back in time than ever before. By observing the light from distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that existed during the universe's formative years. The concept of redshift, a key tool in cosmological research, plays a pivotal role in these investigations. Redshift refers to the phenomenon where light from distant celestial objects shifts to longer wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable information about an object's speed and distance relative to Earth. Through meticulous analysis of redshift data, scientists can determine the size, age, and evolutionary stage of galaxies observed by telescopes like JWST. However, interpreting redshift measurements requires precise calibration and comprehension of potential sources of error, such as instrumental limitations and gravitational lensing. In addition to studying individual galaxies, astronomers are also investigating larger structures of the universe, such as galaxy clusters and superclusters. These vast assemblies of galaxies, bound together by gravity, offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement and velocities of galaxies, researchers can trace the structure-forming filaments of the cosmic web, which spans across the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang. As the universe expanded and cooled, the intense heat of the early universe diminished, leaving behind this pervasive background radiation. Detailed measurements of the CMB's temperature variations offer a snapshot of the universe's infancy, revealing primordial density fluctuations that eventually led to the formation of galaxies and cosmic structures. Satellite missions like the Planck Observatory have mapped the CMB with unprecedented precision, confirming key predictions of the Big Bang theory while also revealing anomalies that challenge the current cosmological paradigm. One such anomaly is the presence of cold spots and unusually large voids in the CMB maps, hinting at unexpected patterns in the early universe's density distribution. These anomalies have sparked debates among cosmologists, prompting alternative theories such as inflationary cosmology, which suggests that the universe underwent a brief period of exponential expansion in its earliest moments. The effort to comprehend cosmic structures extends beyond traditional astrophysical methods. Particle physics, particularly experiments conducted at high-energy colliders like the Large Hadron Collider, LHC, attempts to simulate the extreme conditions of the early universe to probe fundamental particles and forces. Theoretical frameworks such as quantum gravity and string theory offer speculative possibilities for integrating quantum mechanics and gravity, the two pillars of modern physics. These ambitious theories aim to unify our understanding of the universe at its most fundamental level, potentially reconciling the contradictions between Einstein's general relativity and quantum field theory. Meanwhile, the search for dark matter and dark energy continues to captivate cosmologists. Dark matter, hypothesized to constitute about 27% of the universe's total mass and energy content, exerts a gravitational pull on galaxies and cosmic structures despite emitting no detectable electromagnetic radiation. Its elusive nature has spurred numerous theoretical and observational efforts to identify its components and understand its role in galaxy dynamics. Similarly, dark energy, which makes up roughly 68% of the universe's energy density, drives the universe's accelerated expansion observed in recent decades. Its origin and properties remain mysterious, posing profound questions about the nature of the universe and the fundamental forces governing cosmic evolution. The pursuit of these fundamental questions requires interdisciplinary collaboration and the convergence of observational, experimental, and theoretical approaches. Cosmologists, astrophysicists, astronomers, and particle physicists work together to decode the cosmic story written in the universe's structure and light. In conclusion, our investigation into the universe is a journey of discovery and re-evaluation, evidence of human curiosity and ingenuity. From the early pioneers of astronomy to modern-day scientists peering through space telescopes, each generation adds new chapters to our cosmic narrative. As we continue to unravel the mysteries of galaxies, dark matter, and the cosmic microwave background, we inch closer to understanding our place in the vast expanse of space and time. The future of cosmology and space exploration. The relentless pursuit of knowledge about the universe has driven humanity to develop ever more advanced instruments and methods for exploration. From ground-based observatories to space telescopes and interstellar probes, the tools of modern cosmology allow scientists to investigate the most fundamental questions about the cosmos. Next-generation telescopes and observatories. While the James Webb Space Telescope, JWST, has already revolutionized our understanding of the early universe, a new wave of telescopes promises even greater discoveries. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the 2030s, will provide unprecedented insights into dark energy, exoplanets, and the structure of a universe. Meanwhile, ground-based observatories such as the Extremely Large Telescope, ELT, in Chile and the 30-meter telescope, TMT, in Hawaii will push optical and infrared astronomy to new heights, allowing astronomers to observe faint galaxies and analyze the atmospheres of distant planets. One of the most exciting prospects in observational cosmology is the Square Kilometre Array, SKA, a massive radio telescope currently under development in Australia and South Africa. SKA will enable astronomers to map the distribution of hydrogen across cosmic history, shedding light on how galaxies evolved and providing deeper insights into the cosmic web structure. The search for extraterrestrial life. Beyond studying the large-scale structure of the universe, astronomers are increasingly focused on the possibility of life beyond Earth. The discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has transformed astrobiology into a thriving field of research. Instruments like the JWST and upcoming missions such as the European Space Agency's Ariel will analyze the atmospheres of exoplanets, searching for signs of water, oxygen, and other potential biosignatures. The search for extraterrestrial life is not limited to exoplanets. Within our own solar system, moons such as Europa, Jupiter, and Enceladus, Saturn, possess subsurface oceans that may harbor microbial life. Upcoming missions, including NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, will investigate these intriguing worlds, analyzing their ice-covered oceans for signs of habitability. The role of artificial intelligence in astronomy. The vast amount of data collected by telescopes and observatories has led to the increasing use of artificial intelligence, AI, and machine learning in cosmology. AI-driven algorithms are now essential for analyzing astronomical datasets, identifying patterns, and detecting anomalies that could point to new discoveries. From classifying galaxies to detecting exoplanets and gravitational waves, AI has become an indispensable tool for modern astronomers. In the coming decades, AI will likely play a crucial role in autonomous space exploration, helping robotic probes navigate distant planets, analyze samples, and even assist in real-time decision-making for future human missions to Mars and beyond. Interstellar exploration and the future of space travel. While current space missions are confined to our solar system, interstellar exploration remains one of humanity's most ambitious goals. The Breakthrough Starshot initiative proposes sending ultralight, laser-powered spacecraft to the Alpha Centauri star system, the closest stellar neighbor to our Sun, within a few decades. These light sail probes, propelled by powerful Earth-based lasers, could reach speeds of up to 20% the speed of light, enabling them to reach Alpha Centauri in just over 20 years. The prospect of human interstellar travel remains distant, but advancements in nuclear propulsion, antimatter engines, and even theoretical warp drive concepts could one day make such journeys feasible. For now, missions like Artemis, returning humans to the Moon, and NASA's long-term Mars exploration plans mark the first steps in establishing a human presence beyond Earth. Cosmology and the ultimate fate of the universe. While cosmologists have made significant strides in understanding the universe's past, its ultimate fate remains one of the greatest mysteries. Three primary scenarios have been proposed. 1. The Big Freeze. Heat death. If dark energy continues driving the universe's expansion at an accelerating rate, galaxies will drift further apart, stars will burn out, and the cosmos will become a cold, dark void. 2. The Big Crunch. If the universe's expansion slows and eventually reverses, all matter could collapse back into a singularity, potentially leading to another Big Bang.